students, welcome to the video lecture series of Digital Fundamentals. I am your instructor Farnaz Patel and today we'll be learning about binary adders. The content we'll be covering today is binary adder, carry lookup adder and BCD adder. Let's learn about binary adder. A binary adder or parallel adder is digital circuit that performs the arithmetic sum of two binary numbers provided with any length. Which simply means in the previous part we have seen that half adder and full adder adds only 1-bit numbers, which means if we want to add A and B, A must be of 1 bit and B must be of 1 bit, which means A can be either 0 or 1 and B can be either 0 or 1. A and B were only 1-bit number. What if we want to add 2-bit number or 3-bit number or 4-bit number? So for that we use parallel adder. It performs the arithmetic sum of two binary numbers provided with any length. A binary adder is constructed with the help of full adder circuits connected in series, which means for every 1-bit number there will be one full adder, which means to add every 1-bit number there will be one full adder. The output of these full adders will be the carry and sum. The output carry from one full adder connected to the input carry of the next full adder. Let's see the block diagram of parallel adder. So here C1 will be the initial carry, which will be 0. A1, A2, A3 and A4 are 4 bits, which is a single bit number A. Here, as shown in the figure, C1 is input to the first full adder. So C1 will be initial carry, which will be 0. A1, A2, A3 and A4 is single 4-bit number, and B1, B2, B3 and B4 will be a single 4-bit number. So for first bits, for A1 and B1, first full adder will be used. That full adder will produce sum S1 and carry C2. Now this carry C2 will be input to the second full adder, which also accept the inputs of A2 and B2, which is the second bit of the number. So it will add A2 and B2 plus C2, which was previous carry, and generate S2 and C3. Now C3 is input to the third full adder, and A3 and B3, which is third bit of the numbers, will be the input to this third full adder. It will produce the output S3, which is sum 3, which is third bit of sum, and carry 4. Now this carry 4 will be the input to the fourth full adder, and A4 and B4 also will be the input to this full adder. Now this full adder will generate the sum S4, which is fourth bit of the sum, and it will also generate the carry C5. We can say that the C5 is the fifth bit of the sum. This is the structure of the binary adder or parallel adder, which adds the numbers which have more than 1 bits present. Here we note that to produce carry C2, we have to wait for carry C1. C2 is generated by the first full adder, carry C3 is generated by the second full adder, carry C4 is generated by the third full adder, and carry C5 is generated with the help of the fourth full adder, which simply means each and every adder have to wait for its previous carry. To generate sum S2, second full adder needs the carry C2. Then and then the sum output can be generated. To generate S3, the third full adder must have to wait for the carry C3. And to produce sum 4, which is S4, the fourth full adder must have to wait for carry C4. So this will delay this whole process of addition. To remove this disadvantage and to reduce the delay, we will use carry look ahead adder. So this carry look ahead adder reduces the propagation delay by introducing more complex hardware. Here in the carry look ahead adder, we will generate all the carries in advance. So let's learn about the whole process. How can we generate these carries in advance, which means we will generate C2, C3 and C4 in advance to reduce the propagation delay. On the screen, the logic diagram of full adder using two half adder is shown. It accepts three inputs, which are AI and BI. I denotes the relevant bit of that number, which means if we want to add first bit, AI and BI will be A1 and B1. The third input is CI, which denotes the current carry, that will be C1. As we know, AI XOR BI is the sum of this half adder. AI XOR BI can be denoted with the help of PI, and AI dot BI will be equals to GI. Now, carry and PI is connected with the AND gate, and this GI and the output of this AND gate will generate the carry CI plus 1. Also, the carry and PI is connected to the XOR gate, which will generate the sum Si. So Pi is denoted by Ai XOR Bi, which is carry propagate, and Gi is equals to Ai Bi, which is carry generate. Here Gi is called carry generate because it will generate the carry when Ai and Bi both will be equals to 1. And Pi is carry propagate because it is the term associated to propagate the carry Ci to Ci plus 1. So we can denote Si, which is sum, is equals to Pi XOR Ci. And from the diagram, we can say Ci plus 1 is equals to Gi plus Pi Ci. From the above equation, we can derive that to generate C2, which is carry 2, we have to add G1 and P1 C1. To generate C3, we have to add G2 and P2 C2. Now from the above equation, C2 is G1 plus P1 C1. So we can write it like G2 plus P2 G1 plus P1 C1, which will be equals to G2 plus P2 G1 plus P2 P1 C1. Same way, the equation of C4 will be G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 and C1. This is a diagram of look ahead carry generator or carry look ahead generator. This diagram is created with the help of the previous equations. So to generate C2, we will AND the P1 and C1, and then we will OR it with the G1. So this will generate C2. Same way, with the help of the equations, we can generate C3 and C4 by connecting the relevant terms. This is a diagram of 4-bit full adders with look ahead carry. First, we will generate the carry propagate and carry generate with the help of the XOR gate and AND gate. So we will get P1 G1, P2 G2, P3 G3 and P4 G4. This block will contain the circuit of look ahead carry generator. This look ahead carry generator will generate the carry C2, C3 and C4. This look ahead carry generator will generate carry C2, C3 and C4 in advance. So with the help of these carries, we will generate S1, S2, S3, S4 and C5, which can be denoted as S5, the fifth bit of the sum. So this is how we can reduce the propagation delay of the 4-bit full adder, which was the parallel adder. So the use of the look ahead carry adder is to reduce delay of the parallel addition. Next is BCD adder. So we know that BCD stands for binary coded decimal. The minimum requirement of BCD code is 4-bit. Also, we know that the valid range for BCD code is 0 to 9. So BCD adder will add 2 BCD numbers. Now the maximum number for BCD is 9. So the maximum of the first number will be 9 and maximum of the second number will be 9, which means if the number A and B are the inputs to the BCD adder, number A can represent maximum 9 and number B can represent maximum 9. So for that, the addition will be 9 plus 9, which is 18. Also, if there is any carry produces from the previous adder, it will be added to the current adder. Maximum carry will be 1. So the possible output of this BCD adder will be 9 plus 9 plus 1, which is A plus B plus 1 is carry equals to 19. When we directly add A and B, we will get the binary sum. The addition rule for the BCD adder is that if the number is greater than 9, we have to add 6 to it. And if the number is less than 9, the number will be as it is the binary number. So to implement this logic into the logic diagram, let's look at the truth table. So here in the truth table, one side is shown for the binary sum and other side is shown for the BCD sum. For this truth table, as explained in the previous slide, it will have 0 to 19 combination. So for binary sum, 0 to 15 will be 1, 1, 1, 1, which is Z8, Z4, Z2 and Z1. From the 16th combination, there will be carry K. So the 16 will be 1, 0, 0, 0. For 17, it will be 1, 0, 0, 1 and so on. For BCD sum, the valid digits are 0 to 9. So 0 to 9 number will be as it is the binary, which is S8, S4, S2 and S1. From 10 to 19, carry C, which is the carry bit of the BCD sum, will be 1. So for 10, we will write it 1, 0, 0, 0. For 11, we will write 1, 0, 0, 1. Same for 19, we will write 1, 1, 0, 0, 1. So here S8, S4, S2 and S1 will represent 9 and C will represent 1, which will make 1, 9, 19. Now we have to produce the equation for the carry C, which is the carry of the BCD sum. To produce this carry, we have to look at the binary sum. Here we have to write equation for C is equals to 1. For 10 to 19 combination, carry C is equals to 1. So for K is equals to 1, 1, 1, 1, which is shown in the red, will be the part of the equation C. So we can write it directly like K, which is binary sum carry. Plus, we notice that for Z8 and Z4, from combination 12 to 16 are 1 and these outputs are also 1 for C, which is carry bit of BCD sum. So we will write it like Z8, Z4. So the equation till now is C is equals to K plus Z8 and Z4. Now for Z8 and Z2, which is shown in the green part, BCD sum carry C is 1, 1. So we will write it like Z8 dot Z2. Final equation of BCD sum carry C will be K plus Z8, Z4 plus Z8, Z2. Now from this equation, we have to make the logic diagram of BCD adder. Here, two numbers A and B will be the input to the 4-bit binary adder. So A will be a 4-bit and B will be a 4-bit. This addition will be the binary addition and it will produce the binary sum Z8, Z4, Z2 and Z1. Also, it will produce the carry K. Now, as per the BCD rule, if the addition of these two numbers is greater than 9, we will add 6 to it. So we have to generate the carry C, which is BCD sum carry will be generated with the help of equation C is equals to K plus Z8 Z4 plus Z8 Z2. So in the first AND gate, we have connected Z8 and Z4. In the second AND gate, we have connected Z8 and Z2. And then this outputs will be ORed with the carry K, which is the carry of the binary sum. Now this will generate the carry C, which is the carry of BCD sum. This carry C will be equals to 1 if the binary sum is greater than 9 and it will be 0 if the binary sum is less than 9. Now if the sum is greater than 9, we have to add 6 into the original binary sum. So for that we need another 4-bit binary adder. The first and the last bit will be 0 and C will be the input to the 4-bit binary adder as the bit 1 and 2. So the input to this second 4-bit binary adder will be original binary sum, which is Z8, Z4, Z2 and Z1 plus 6, which is 0, 1, 1, 0. If the sum is less than 9, the added number will be 0, 0, 0 and 0. So this will produce the BCD output S8, S4, S2 and S1. This is the diagram of BCD adder. So in this lecture, we have learned about the binary adder, which is also called as parallel adder, carry look ahead adder and BCD adder. This is the end of our second module, which is combinational logic circuits. Thank you.